Okay, so here's the physics review. So chapter 15, we talked about Coulomb's law. And what that did is it told us that there was a force between two charged particles, which was equal to Coulomb's constant times the product of the two charges involved, divided by the distance between the two charges. And we did this problem in class, and the test question will be similar to this. Well, it'll be like the ones we did in class, just with some different dimensions. So we'll have three charges for the force calculation. So this will be Q1, Q2. Let's use A instead, so that they don't. So we'll call this charge A, call this charge B, call this charge C. And this has charge Q sub A, this has charge Q sub B, and this has charge Q sub C. And in the problem we did in class, we found the forces on all the charges, but we're not going to have time to do that. So what I will ask you is, what is the force of force due to charge A on C, and the force of charge B on C, and you can calculate those by just using the appropriate charges and use the values, the magnitudes and not the signs, and then the distance will be the distance from here to there, and for this particular one, and then in the second case you'll have Q sub A, actually Q sub B and Q sub C. And again, if they're negative charges, make them positive in this part of the calculation. And make sure you get these subscripts right. And this distance will be from A to C, and this one will be from B to C. And the distances are always positive numbers. Now the question is the sign, plus or minus, question mark. And you do that by looking at what is the interaction between the charges, either the same sign or the different sign charges. And if they're the same sign, then there's a repulsive force. So for example, if this one had the same sign as that one, then they would repulse and the force would be in that direction. So you use a positive value. Let's say these two have different signs. So this would be the direction of force of A on C. Let's assume this one's positive, this one's positive, and this one's negative. So these two forces, they're the same sign, so they're repulsion. So that pushes it that way. And then compare these two, you've got negative and positive, so there's an attractive force. So this would be the force of B on C. So that would be a negative result. So then if I asked you to find what is the force on C due to both those forces, you would just add them together. The force of A on C plus the force of B on C. The sum of those two would give you the answer. Now I'm not going to, you're going to have to think about, understand this. There's not going to be some just, I'm going to be able to plug the numbers in and get the sign right. You just have to think about, are they attraction? Is it an attractive force or is it a repulsive force? Okay, you can look back on your thing we did in class for that. Now, let's say we'll talk about electric field. So there's two ways of doing this same problem with electric fields. One is what you would do is you would take, to find the electric field at point C, so what you would have in this case, let me just copy all this stuff here. So the difference when dealing with electric fields is you don't have a charged particle here. So we take that particle out and we just say there's a point in space. So the question is, what is the electric field? And I'm going to show it as a vector because the sign will tell you what direction it's going at point C, question mark. So the electric field, there's two things. It's equal to K times Q. Let's say the electric field at point, so let's erase this here a second. So we'll say the electric field at C due to A. And then there'll also be the electric field at C due to charge B. So how do you calculate those things? So the electric field is going to be force per unit charge, so instead of having charge C in there, we don't have it. We still have the plus or minus question. So it's going to be K times the magnitude of charge A divided by R AC, which is from charge A to point C, and you square that. And again, that distance is going to be positive. Distances are always positive. And then you're going to have plus or minus K times charge B divided by the distance between charge B and point C. And you square that. So all we've done is divide by the charge C, but in the case of electric fields, it's always positive. So it turns out in this case, looking at our previous force example, that the direction of the electric fields are going to be the same as they are here. Now if I had done the force calculations and this was a negative charge, then the forces would be exactly opposite. But let's use red again. So what you would have is you would have the electric field, I'm just going to say C due to A, and the green here is the electric field at this point on C due to charge, which one is that? That's B. So this is due to A, this is due to B. So for this particular example, where this is negative and this is positive, these are the directions that would result. So this one would be a positive and this one would be a negative. So to get the combined electric field at C, what you're going to do is you're just going to add those two together when you have them right. I'll put a vector in here because we do show the direction by the sign. So it's going to be the electric field is C at C is the electric field at C due to A plus, so it's at C due to A plus the electric field at C due to B. And again, the red one, this first one, A, is going to be a positive number, and this one's going to be a negative number. You add them together and you get a result, which is going to be either positive or negative, depending upon which one of these is larger. That's one way of doing it. The other way to calculate the electric field at C is to take the force at C, which we've calculated in the first thing right here, the force on C, and you divide by the charge at C from the first part of the problem. And you don't use the absolute value because that'll determine whether this changes sign relative to the force or it's the same direction. So in this case, because QC was positive in our original calculation, the sign of the direction of the electric field is going to be the same direction as the force. But if this were a negative charge, then the force would be in an opposite direction from the electric field. So there'll be something like that, where you have to do it in a line. Then I'm going to put in a voltage question. In that case, we did this in class, so it's nothing new, but in the case of voltage, I'm going to do it in 2 dimensions. So this will be X and this will be Y, and what I'll do is I'll give you, let's say I give you the charge at 2 points. So this is point C. This is where I want to find the voltage. And here I'll give you the coordinates. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this is 6, 6, and this one is 2, negative 4, and this one is, I think it's the same thing. 1, 2, 3, 4, 5. So it's going to be negative 5, 6. So those are the coordinates, and this has some charge. We'll call this point A, and this is point B. So there'll be some Q sub A and there'll be some Q sub B. Now at C there's no charge. What I'm trying to do is figure out, what is the voltage at point C. So again, we need to know the distance between these 2 points from here to here, and we need to know the distance from here to here. So this distance will be R AC, and this one will be R A B. So we can do the same kind of thing that we did before. The voltage at C due to the charge at A, and we'll also do the voltage at C due to charge B. So the voltage is Coulomb's constant times the charge. So it'll be the charge at A divided by the distance from A to C. Now we don't square it. And the same applies here. So it'll be K times Q sub B over R sub BC. So we can figure these out from the Pythagorean theorem. We'll know this distance, we'll know that distance. So this squared plus that squared equals that squared. And in this case, we don't take the absolute value of the charge. We don't have to worry about that. That's the nice thing about voltages. We'll use whatever charge it is. So let's say this one is positive, this one is negative. So here it'll be positive so many coulombs or microcoulombs, and this one will be negative so many microcoulombs. The distances are always positive. So this is positive, this is positive, that's positive, that's positive. This can be plus or minus depending upon what's given in the problem. And then to find the voltage at C due to both charges, you just add the 2 voltages together. So it's at C take our previous 2 answers that we'll have here. At C due to A plus the voltage at C due to B. And if one's plus and one's minus, then depending upon which voltage is larger, it'll either be plus or minus. Okay, so that's the voltage calculation. Now, we looked at capacitors, just in general capacitors. So the capacitors are 2 parallel plates separated by a distance d. The the plates have a certain cross-sectional area, and they both have the same cross-sectional area. And what happens is, you know, we connect the lines to it and put a battery like we did in class. So here's a battery, here's a positive terminal, here's a negative terminal. And what happens is we get electrons on this plate, and we get the absence of electrons on this plate. And what that does is it creates an electric field that goes from the positive side to the negative side. And if the plates are close enough, then it's a uniform electric field. So the electric field between the plates is just equal to the voltage. Make sure I get the units right here. Actually, the electric field is it's going to be, so you have, you know, is it divided by the distance or is it multiplied by the distance? So you have to think about this. You know, we talked about in class that the electric field is stronger if these charges are closer to each other. So the smaller this distance for a given voltage should give you a stronger electric field. So that makes sense. And it probably does for me, you know, the base calculations as well. Yeah, let's just prove that's true. So here you have K, and you have charge divided by R squared. And here voltage is K times Q divided by R, and then you divide by R, which is going to give you KQ divided by R squared. So that makes sense as well. So the electric field, the value of the electric field between these parallel plates is the voltage on either plate, which is caused by this battery, divided by the distance. The smaller that distance. So if I give you a capacitor problem, I might give you the voltage and the distance, and then I ask you to find the electric field. So it's a pretty simple calculation. You know, if it's 5 volts and the distance, so this is the voltage, the distance is equal to 0.001 millimeters, then the electric field is just going to be equal to 5 volts divided by 0.01 millimeters, and then you'd to get to the number of meters, you'd multiply by 1,000th, and so that's equal to 5. This is 1 times 10 to the negative 2. This is 1 times 10 to the negative 3. So you get 1 times 10 to the negative 5, which is 5 times 10 to the 5th. And the units are volts per meter. Electric field is also newtons per coulomb. And that's because electric field is force divided by charge. Okay, so that's one thing about capacitors. The second thing is the definition of capacitance. That's equal to charge divided by voltage. And the units for charge are coulombs per, the units for potential, we call it potential, but it has units of volts. So it's coulombs per volt, and we call that a farad. And remember, if you're given a capacitance like 2 times 10 or 2 microcoulombs, a lot of times things are microcoulombs, that's going to be 2 times 10 to the minus 6 coulombs. So you got to always convert. This is just a way of more easily writing it instead of 0.000002. You just have to remember to multiply it by 10 to the minus 6th. If you had C is equal to 5 millicoulombs, that would be 5 times 10 to the minus 3 coulombs, micro. was 10 to the minus 3. There's pico and there's nano. We're not going to worry about those right now. So that's the just the relationship or definition of capacitance. And then we have the equation for capacitance as a function of the variables. So you have mu 0 times the area divided by the distance. So that's how you figure out what the capacitance is. So if I gave you a capacitor, that I gave you the voltage, the distance is used for calculating the electric field, and the distance is also used for calculating the capacitance. So let's just use the same distance as our previous problem. So that was, so the distance is, we said it was 0.01 millimeters, and we had to multiply by 0.001. That's number of meters per millimeter. So that's 1 times 10 to the minus 5 meters. So that's distance. And if I'd have to give you an area, so let's say the area is 50 centimeters squared. So we'd have to convert that to meters squared. So what you do is you have 50 centimeters squared, which 50 centimeters is 0.5 meters squared, which would be 0.25 meters squared. Something's wrong here. That's not right. Let's try it again. Okay, so it's 50 centimeters quantity squared. So it's the units that are squared. So you'd have 50, and you have 0.01 meters per centimeter. So we have 50 centimeters squared, and you have 0.01 meters per centimeter. And then you square that to get into centimeters squared. So that would be 50 times 0.01 squared, and the units there would be meters squared. So I need to get my calculator. Okay, I found it. So 0.01 squared times 50 is we have to get the area in meters, so that's 0.005 meters squared. Another way to think about it is you just take 50 divided by 100 squared, and you get the same number. And mu 0, put this on your cheat sheet so you don't have to look it up. This mu 0 is equal to 1 over 4 pi times k. And remember k, I'm going to write both of these down here. So Coulomb's constant is, use this value in your calculations, 8.99 times 10 to the 9th. And the units are newtons meters squared per coulomb squared. Mu 0, which is 1 over 4 pi k, is, and you don't have to go through the calculation, is actually, it's epsilon 0. I did that wrong. Mu is some other. Is that right? Yeah, it's epsilon 0. Mu is for magnetism. So that's epsilon 0. Anyway, 1 over 4 pi k. So epsilon 0 is 8.85 times 10 to the minus 12th, and the units are the reciprocal, coulomb squared per newton meter squared. So use this for calculating the capacitance, use this for calculating forces and electric fields and voltages. Okay, so let's calculate the capacitance. If we have a capacitor that has this spacing between the plates, has this area, and this epsilon 0, which is always the same. So we get 8.85 times 10 to the minus 12th coulomb squared per Newton meter squared times the area, which is 0.005 meters squared, divided by the distance, which is 1.0 times 10 to the minus 5 meters. And you get capacitance, which is farads. And usually these numbers are pretty small. So I get 4.4, we'll just do two significant figures, times 10 to the minus 9th farads. Okay, so I'll probably give you a problem where you have to, make these calculations. Then you're going to have one, or these are all possibilities. I may not put everything on here, but capacitors in parallel and series. We did that in class, so you can look at that handout. What I'm going to ask you to do is to take a group of capacitors and reduce those down to a single capacitor. So you're going to end up with an equivalent capacitance. And then you can use that equivalent capacitance to calculate the equivalent charge by using the definition of capacitance. So C is equal to Q over V. So the charge is the equivalent capacitance times the voltage that's applied to that equivalent capacitance. Now you're not going to have to go all the way back and figure out all the charges and all the voltages because you just don't have time. So just be able to reduce it down. The same thing applies for resistors. So I will give you some combination of resistors, and you need to calculate the equivalent resistance of all the resistors. And then what you can do is you can use that with the given voltage again to calculate the equivalent current. And the current is equal to, well, that you get that from Ohm's law. Ohm's law says it's voltage per current. So to get current, it's going to be voltage divided by the equivalent resistance. So there'll be some battery, and you'll get the current. And remember, the units for current are amps. The units for capacitors, farads. The units for resistors is ohms. So we use an ohm sign for that. We use an F for that. We use an A for amps. So we did those in class. Let's see what else am I going to put on there. Or is there anything I wanted to put on there? Oh, today we talked about the charge as a function of time. These are on a capacitor. And this is an RC circuit. So we have one resistor and one capacitor. So for the capacitor, we saw that the charge was equal to the input voltage times the capacitance times 1 minus e to the minus t divided by RC. And we saw that the voltage as a function of time was equal to the battery voltage times 1 minus e to the minus t divided by RC. So those are the voltages and charge on the capacitor. And we did that by solving a first order linear differential equation. For the resistor, we have V of t, voltage across the resistor, which just ends up being e to the minus, well actually it's Vn, so it's the voltage that we supply times e to the minus t over Rc. So when t equals 0, you get the maximum voltage, and then when t goes to infinity, this goes to 0, whereas this one goes to Vn. And then we have the current as a function of time. Current is voltage divided by resistance. So we just have to divide that by R. So those are the four equations that define the voltage across each element and the charge across each element. So just be able to, if I give you voltage, capacitance, resistance, and I say at time something, times t equals some seconds, to be able to calculate all these quantities. And you have to remember at any time that this plus that has to equal the input voltage. I'm going to give you a take-home problem associated with Kirchhoff's laws, so I'm not going to talk about that now, but it'll be, similar to what we did in class. So that'll probably be worth about 25% of the grade. And I think that's enough to keep you guys busy, at least. So let's go back, review here. Straight line charges, calculate the force on a third charge due to two other charges. Calculate electric field at a point C due to two other charges. Calculate the voltage at a point due to charges at two other points. Determine the electric field between the plates, parallel plates of a capacitor. Calculate the, given the voltage, there's the definition of capacitance. So if I gave you the capacitance of the voltage, you should be able to calculate the charge. If I give you 2 out of 3, make sure you can calculate the third one. Just simple rearrangement of that equation. The capacitance of two parallel plates based on the area and the distance between the plates, and this constant is using that. Right, make sure you write down E's, epsilon 0, and K, so you have it to use. So this is calculating the capacitance given these three things. So simple calculation. Reduce capacitors in parallel and series into an equivalent capacitance. Same with that. Let's just write those down for you so you don't forget. So this is for capacitors. Say caps. So series and parallel. So for capacitors in parallel, you just add the capacitances together of the different capacitors. For series, you say 1 over the equivalent capacitance is equal to 1 over the sum of 1 over the individual capacitances. Like that. Okay, so that's capacitance. Now for resistors, they're the opposite. So the equivalent resistance of resistors in series is just the sum of the resistors in series. And for parallel resistors, it's 1 over the equivalent resistance is 1 over each one added together. So just review your handouts and make sure you have the formulas available so you don't forget them. And then finally, the time equations for capacitors and resistors in an RC circuit.